Okay, so what are these intermolecular forces? Well, their strength depends on the structure of the particles, and then the state of matter depends on how strong those forces are. If the forces are strong, then you're going to have high melting and boiling points. The intermolecular forces are the forces that hold the molecules together in the solid or liquid state. In order to make a gas, you have to give it enough kinetic energy to break loose from those attractions. So the stronger those forces are, the more heat you have to put in to cause it to get into a gas state. And so the boiling point will be higher, and so will the melting point. So if forces are weak, we have low melting and boiling points. All of these intermolecular forces come about from interactions between charges, partial or temporary charges on particles. So it's the attraction of positives and negatives. And so Coulomb's law, which we've seen before, can help us with this. The energy of attraction is proportional to the product of the charges divided by the distance between them. So if we have larger charges, we have a stronger attraction. If we have a shorter distance, we have a stronger attraction. It can be easy to confuse bonds with intermolecular forces. So here's two water molecules. Right here, this is a bond, a covalent bond within the water molecule. Has a bond length of 96 picometers. Intermolecular forces are operating at much greater distances. So might be more like 300 picometers. I think I missed it somewhere. But the very name here, intermolecular. So inter means between. Intra means within. So intramural sports are when you have different teams at the same school. Intervarsity sports are when you have teams from different schools competing against each other. So these are between the molecules, not within the molecules. So the first one, which is the weakest, is called the dispersion force. All molecules and atoms have dispersion forces. It's also called a London force, or a London dispersion force, or an induced dipole force, or a van der Waals force. It's got a whole bunch of names. I'm going to try to stick with the one the book uses, dispersion force. So here we have an illustration of a helium atom. We've got the 2 electrons, and there's 2 protons and neutrons in there. And so imagine that we're taking pictures of this helium atom. When we observe it, then we force the electrons to behave like particles, and we can see where they are. So here we've got one down there and one up here, and a little bit later there's one over here and one over there. Much of the time, they'll be kind of spread out on opposite sides. But occasionally, they'll both be on the same side of the helium atom because they're moving independently of each other. So here, with the 2 electrons on one side, now this atom is a little bit lopsided. It's going to have a partial negative charge over here because all the electrons are there. And it's going to have a partial positive charge over here because this is just exposed protons. And so that's what's called an instantaneous or temporary dipole. And they're very, very brief. It comes and it goes. It comes and goes, comes and goes. Just instantaneous dipole. So if we have an instantaneous dipole on one atom, that can cause or induce a dipole in a neighboring atom. So here's the one that was lopsided just by chance, right? Partial negative, partial positive charge. This partial positive charge on the first atom is going to attract the electrons of a neighboring atom. And that's going to form an attraction between the 2 atoms. And this attraction is the dispersion force. So this one induces a dipole on that one. This one induces a dipole on that one, and it goes around like that. But then this one's dipole disappears, and that guy's like, oh, it's gone, and he disappears, and it all goes away again. Any questions? The strength or the magnitude of the dispersion force depends on how easy is it to get the electrons in this thing lopsided. How are they held really tight around the nucleus, or are they big and kind of floppy, right? So if you get a larger electron cloud, it's easier to polarize because the electrons are held less tightly, because the larger the cloud, the further away they get from the nucleus, and so they're more easy to polarize. And so we see, looking at the noble gases, helium is the smallest, and as we go down the column to xenon, xenon is larger. Xenon's electrons are easier to polarize. And so we can see the effect of this by looking at the boiling points. Helium boils at 4.2 Kelvin. Xenon boils at 165 Kelvin. The increased boiling point demonstrates that the forces of attraction between xenon atoms are greater than between helium atoms. And that's generally related to the molar mass. So you see molar mass also increasing. The shape of the molecule also plays into this. Here we have two versions of pentane. N, or normal pentane, and neopentane. Same chemical formula, same molar mass, but they have different boiling points. This one boils at 36, and this one boils at 9.5 degrees Celsius. So what's going on there? Well, both of these have dispersion forces. We can't say it's due to a difference in molar mass because they're the same mass. It's due to a difference in shape. N-pentane has this longer, more cylindrical shape. And so we can have two of these molecules together like two cylinders, and there can be more space, more area where they are touching. Whereas the more spherical neopentane, two spheres can only touch at a single point. So if you imagine these as being covered in Velcro, these two are going to stick together much better than these two, right? Because the surface area where they stick is larger. That makes sense? Here we're looking at straight chain alkanes, looking at the boiling point as a function of the molar mass. And as we increase the size of these, the boiling point goes up. Because here we have nonane. Nonane is longer, it's got more surface area, and its electrons are more easily polarized. And so this one has stronger dispersion forces than pentane does. So there can be questions like this on the fourth exam or on the final exam. Which halogen has the highest boiling point? Well, so let's look at the halogens, right? We've got chlorine, and under it is bromine, and under that is iodine. And we just learned that dispersion forces depend on what? Molar mass. So larger molar mass, big floppy molecule or atom, and so its electrons just, can kind of, it's like Santa Claus with his belly like a bowl full of jelly, right? As opposed to one of the little skinny elves, right, that has no body fat at all. So which of these has the largest molar mass? Iodine. So that should have the higher boiling point. There's another way you can answer this particular question. So the periodic table on the wall is color-coded by state at room temperature. And so chlorine is red. Chlorine is a gas at room temperature. Bromine is blue. It's a liquid at room temperature. Iodine is black. It's a solid at room temperature. And And so we can see just by their states of matter that iodine has a higher boiling point than bromine and chlorine. The next type of force is called the dipole-dipole force. And this is present in all polar molecules. It's stronger than the dispersion force because instead of a weak dipole that's just there temporarily, here we have an actual dipole that's always there, and so the attraction is always present rather than coming and going and coming and going. So polar molecules have permanent dipoles, and this is part of why we needed to learn how to identify which molecules are polar and nonpolar so we can predict what kind of forces they have and relative boiling points and things like that. So here we have a space-filling model and an electrostatic potential map of polar molecule. And so here's the oxygen. It's more electronegative. This is the negative end, and this is the positive end. So the negative end of one molecule is attracted to the positive end of the other, and this dotted line here is representing the dipole-dipole force. Polar molecules also have dispersion forces, and so their boiling points will depend on molar mass as well. But when we're comparing, we have to be careful that we're not changing multiple things at once. So here what we're going to do is we're going to compare formaldehyde and ethane. And because we don't want the dispersion forces to cause a difference here, these are two compounds that have extremely similar molar masses, right? Almost the same. These are their structures. Here in ethane, we have carbon-hydrogen and carbon-carbon bonds. Are either of those polar? No. No polar bonds, right? And also, if we use my shortcut rules, you look at a central atom, no lone pairs, right? And everything bonded to it is essentially the same because this is not a polar bond. So up here, we have no lone pairs, but now we have two hydrogens and one oxygen. That guy's lopsided. Oxygen has a higher electronegativity. He's going to pull the electrons away from the hydrogens. And so this oxygen end is going to be a partial negative charge, and the hydrogen end is a partial positive charge. This is a polar molecule. They both have dispersion forces. Their masses are the same, so the strength of the dispersion force is going to be the same. But this one also has dipole-dipole forces, whereas this one does not. So if we look at boiling point, this one boils at negative 19 degrees Celsius. This one boils at negative 88, which is much lower. So this has weaker intermolecular forces holding it together. Any questions? Here's looking at boiling point as a function of the strength of the dipole moment. So all of these compounds are similar in mass. But this one is nonpolar. It has a very, very small dipole moment. And as we go across here, the dipole moment, the polarity becomes greater and greater, and we see that that causes the boiling point to increase. Polarity of molecules is very important when we're talking about, are things going to dissolve, are things going to mix in each other? And so this might be a new word for you, miscibility. This is not a word, but it makes more sense than that one does. How about mixability? That's essentially what miscible means, is that they are mixable. So two liquids that are miscible in each other, you can mix them together. You could have a little bit of one and a lot of the other, or a lot of the first one and a little bit of the other. The proportions don't matter. They just mix together freely. And the expression we use to help us remember this is like dissolves like. If you have two substances that are polar, probably miscible. Two liquids that are nonpolar, probably miscible. You can think of those intermolecular forces as being a little bit like the language that those molecules speak to each other. People mix around much better if they're all speaking the same language. If we have a nonpolar and a polar liquid, this is not like dissolving like. We have different here. And so the water molecules are going to be all attracted to each other by their dipole-dipole forces, whereas the pentane molecules over here only have those very weak dispersion forces, and so they're not going to mix together. They don't speak the same intermolecular force language. Well, here's another question. Which molecules have dipole-dipole forces? So before you can answer a question like this, you need to know what kind of molecules, not specifically those, but what sorts of molecules can have dipole-dipole forces? Can nonpolar molecules have dipole-dipole forces? No, they can only have the dispersion forces. What we're looking for here is polar molecules. Polar molecules will have dipole-dipole forces. So we need to be able to identify whether these things are polar or not. So let's sketch out a Lewis structure. So Ci4, and there's no trickery going on here. I'm not trying to trick you. If you want to count up all the electrons, you'll see that you're going to have lone pairs on these iodines. But carbon, with just the 4 bonds, has an octet, and carbon is not large enough to expand its octet. So there's no way that carbon could have any lone pairs, right? So the rules for a nonpolar molecule: no lone pairs on the central atom, check. All atoms bonded to the central atom are the same or have the same electronegativity, check. So this is a nonpolar molecule. Any questions about that? Does it have dipole-dipole forces? No. It only has dispersion forces. Okay, so what about CH3Cl? So C, and there's 3 H's on it, and there's a Cl on it. And the Cl would have lone pairs. Are there any lone pairs in the central atom? No. Are all the atoms bonded to it the same? No. Chlorine's different. So chlorine is more electronegative than hydrogen, so this is going to have an uneven distribution of electrons. It's going to be polar. It's lopsided. It's not symmetrical. So this one's polar, so it will have dipole-dipole forces. How about HCl? These diatomic molecules are the easiest because they only have one bond. If the bond is polar, the molecule's polar. Is this a polar bond? How do we know? Those are 2 different elements. Remember, I said it's good enough for Chem 1A to assume that if these are 2 different elements, there's a polarity, a polar bond there. If they're the same element, like if we have Cl2, we got the same element, they have the same electronegativity, this is a nonpolar bond. But this is going to be a polar bond because the elements are different. Because this is polar, this also has dipole-dipole forces. This is an electrostatic potential map for acetonitrile. And so if we draw the dipole here, the nitrogen end, where the red is, that's more negative, and the other end, where the hydrogens are, is more positive. So if we have 2 of those molecules, how are they going to be attracted to each other? Which of these pairs represents how they would kind of be attracted to each other? Would we have the nitrogen ends being attracted to each other? This is the partial negative end, and this is the partial positive end. Do two negatives attract? No. So if they're oriented like that, they're not going to attract each other. What about this? Well, here we got the negative end, and this one's just kind of sideways. That doesn't look very good. How about this? Here we have a negative end and this negative end, they're kind of overlapping. Or up here, we have the negative end near the positive end. So when they're arranged like this, we're going to get attraction between the two molecules. The third intermolecular force is called hydrogen bonding. And I think of this as super dipole-dipole force, right? It is a dipole-dipole force. It's just much stronger than a regular dipole force. Just like Superman is much stronger than a regular man, right? Superman. So we'll find this in polar molecules that contain hydrogen bonded to F, O, or N. And this is going to give us an especially strong dipole-dipole force because fluorine, oxygen, and nitrogen are very electronegative, and they're also very small. So we have stronger charges, larger charges, and because the atoms are small, they can get closer to each other. So when we're thinking about Coulomb's law, where the energy is proportional to Q1 times Q2 divided by the distance between them. The numerator is larger, the denominator is smaller, both things working to make the force stronger. Okay? So here's looking at, I believe this is HF. So we've got this dipole here, and the negative end of one molecule is attracted to the positive end of the next molecule. And the hydrogen bond is the attraction electrostatically between the molecules. So if we drew the Lewis structure there, this is a bond between hydrogen and fluorine. And so it's very easy to confuse this and say, well, that's a hydrogen bond. Well, that's hydrogen bonded to something, but it's not a hydrogen bond. I don't think this is the greatest name, but we're stuck with it. The hydrogen bond is the attraction between the two particles. It is not the bond with hydrogen. So we need to be able to identify compounds that have hydrogen bonding. And so what we're going to look for is fluorine, oxygen, or nitrogen that is bonded to hydrogen. And this reminds me of the movie E.T. And what did E.T. want to do? Phone home. E.T., phone home. Right? Phone home. Okay? Phone home. Fluorine, oxygen, or nitrogen bonded to hydrogen. So here we have ethanol. So ethanol has an oxygen-hydrogen bond. It needs to be fluorine, oxygen, or nitrogen bonded directly to a hydrogen. So this has that bond that allows hydrogen bonding to occur. Because these dipoles here are stronger than regular dipoles because oxygen is so electronegative. And the distance between them is smaller because these atoms are smaller and they can get closer together. Here we're looking at hydrogen bonding in water. Water has two hydrogen-oxygen bonds. And the hydrogen bond is between the hydrogen of one molecule and the oxygen of a neighboring molecule. These dipoles make them like little magnets, and they're attracted to the opposite kind of magnetism, right? Except it's electric charge instead. So, important to remember, hydrogen bonds are between molecules, not within the molecule. Chemical bonds are within a molecule between individual atoms. They are much stronger than hydrogen bonds. Hydrogen bonds about 2 to 5% the strength of a covalent bond. And we see that compounds with hydrogen bonds have higher melting and boiling points. So if we look at these two guys, ethyl and dimethyl ether, okay, again, we found compounds with the same chemical formula, same molar mass. So dispersion forces are the same, right? These are both polar molecules. They're both going to have dipole-dipole forces. But let's do the Lewis structures here real quick. This is ethanol. We've got the space-filling models, but it's a little hard to see. So there's ethanol, and here's dimethyl ether. And why is that one polar? Because the oxygen has lone pairs. Both of these contain oxygen and hydrogen. But in dimethyl ether, the oxygen is not bonded to the hydrogen. So we don't get that extra strong force called hydrogen bonding. Here, oxygen is bonded to hydrogen, and so this will do hydrogen bonding. And if we look at boiling points, this one boils at 78 degrees Celsius, and this one boils at -22. Much lower boiling point tells us weaker intermolecular forces. Water actually has an extremely high boiling point for what it is. So here on this graph, we're looking at the boiling point of the substance compared to its molar mass. So if we look at the group 4A compounds with hydrogen, there's methane, CH4, SiH4, GeH4, SnH4. What's changing here is the central atom is getting larger, and so the molar mass is getting larger, the dispersion forces are getting larger, and the boiling point is getting higher. And there's kind of a trend, right? If we look at group 6A, we say, well, there's a trend right through there, and we expect that water would be down here somewhere. Tellurium, with 2 hydrogens, is the heaviest. And then selenium, and then sulfur. These molecules may be polar, but can they do hydrogen bonding? No. Because, well, you can't see it because I wrote over it. None of these have fluorine, oxygen, or nitrogen, the phone part of phone home. This has oxygen, and the hydrogen is bonded to it. So this is a much higher boiling point because it has dipole forces, hydrogen bonding in addition to the other forces. Which has a higher boiling point, HF or HCl? And the dreaded question, why? Comparing boiling points like this, you always want to identify what kind of forces do these things have. Do they each have dispersion forces? Yeah, because everything has dispersion forces. So they both got dispersion forces. Are they polar? Yeah. We just got one bond and 2 different elements. These are polar. So if they're polar, they have dipole-dipole forces, right? So I'm going to call that dip-dip because I'm tired of writing. Can either of these do hydrogen bonding? Yeah. So this one can do hydrogen bonds because ET phone home, fluorine bonded to hydrogen. So this will have the higher boiling point, which is not what the mass would predict, right? If you're just looking at dispersion forces, HCl has stronger dispersion forces, but hydrogen bonds are just so much more important than dispersion forces. So you can only go based on molar mass if the kinds of forces are the same. You look at the different kinds of forces first, and then you look at mass. This last one is technically not an intermolecular force. But the Ion-Dipole Force occurs when ionic compounds mix with polar compounds. So an example would be salt dissolving in water. So salt's an ionic compound. You've got the sodium ions and the chloride ions, right? Water is a polar substance. It has permanent dipoles, positive end here, negative end there. The negative ends of the water molecules are going to be, the positive ends are going to be attracted to the negative ion. The negative ends are attracted to the positive ions, right? And so why would sodium and chloride want to separate from each other when they have this ionic bond with each other? Well, it needs to be replaced with something else that's better. Well, one of these attractions is not better, because this is not a full positive charge. It's a partial charge. But if we get a whole bunch of partial charges, could those add up to more than +1 charge? They could, right? And a bunch of water molecules here could add up to more than a -1 charge for the sodium ion. So this is kind of a creepy example, but I think of, sodium and chloride as maybe two little kids that went out to the park, and then people come and they're trying to lure them away. And this one likes candy and this one likes dogs or something. I said it was creepy. This type of force is stronger than the other intermolecular forces. This is a table summarizing all of that. The names, what kind of molecules have them, little diagram, and strength. You don't need to know these numbers, but you should know this order. Dispersion's weakest, then dipole-dipole, then hydrogen bonding, then ion-dipole. Okay, which substance has the highest boiling point? What's the strongest intermolecular force we could have? It can't be the ion-dipole force because that only happens in a mixture. Hydrogen bonding. Can N2 do hydrogen bonding? No. It doesn't have any hydrogen. How about CO? Again, no hydrogen. How about this one? CH3OH. And this is implying that the oxygen and the hydrogen are bonded to each other. So this one has hydrogen bonding. We predict that that one is going to have the highest boiling point. If you compare the molar masses of these, you'll see that they are in the same ballpark. If you threw in something like I2 in here, well, I2 only has dispersion forces, but I2 is much larger than these guys. This one's 28, and this one is 28, and this one I think is, 32 grams per mole. And this guy down here would be like 250-ish, much bigger. So we're not going to give you one like this to compare with those guys, because when you have to compare multiple things at a time, it gets tricky. But how do I know that iodine has a higher melting point or higher boiling point than CH3OH? This is methanol. That liquid that we dissolved our zinc in is a liquid at room temperature. What is iodine at room temperature? It's a solid. But that wasn't in the question. Any questions? Your DNA is held together by hydrogen bonding. So there are two strands in your DNA. Each strand has a backbone of phosphates and sugars. And then on the sugar, there is another thing called the base. There are 4 different kinds of bases: thymine, adenine, cytosine, and guanine. And it turns out that thymine and adenine can make 2 hydrogen bonds with each other. Guanine and cytosine can make 3 hydrogen bonds with each other. If you try to pair guanine with adenine, the polarities don't match up. It doesn't work out. So these guys are always going to pair together, and these guys are always going to pair together. And so in your DNA, if you have a thymine on one strand, you're going to have adenine on the other side. If you have guanine on one side, you're going to have cytosine on the other. And the way your body replicates the DNA is it unravels the original DNA and takes half of that, one of the strands, and starts making a new strand by bringing in the bases that match up with what's on the original strand. And so the bases on the new strand here are opposite of the bases on the original, and same thing here. And so we end up with 2 identical DNA molecules. Very cool, due to hydrogen bond.